welcome to the next part of solving the project Euler problems. And as you can see, we have solved 24 problems along with 67. And today we are going to solve maybe one or two more problems depending on what the problems look like. So let's take a look at the first problem. So problem number 24, and see what, wait, I went to the wrong problem. I went to 14. I need to go to 24. Okay. So this is problem number 24. Let's open a Jupyter notebook and let's start. This is problem 24. Problem 24, and let's put problem 24 over here, and this is lexicographic permutations. That's the name of the problem. So it has to do something with, it will have something to do with permutations. Okay, so now let's read the problem. A permutation is an ordered arrangement of objects. Okay, for example, 3, 1, 2, 4 is one possible permutation of the digits 1, 2, 3, and 4. Okay, so that's one ordering of the digits. So yeah, if all of the permutations are listed numerically, if all of the permutations are listed numerically or alphabetically, we call it lexicographic order. The lexicographic permutations of 0, 1, 2 are 0, 1, 2, 0, 2, 1, 0, 2, 1, 2, 0. Okay. What is the millionth lexicographic permutations of the digits? Okay. So that's basically what we have to solve. So how do we go about solving this? Okay, so let me bring my notebook over and try to solve this problem and see whether we can solve this problem. This looks like an interesting problem. So, all right, let us try to solve this. So if we have, let's start with 0, 1, and 2. There might be something recursive about it. Let's see. I feel that there is some recursion involved over here. Okay, so we have, let's talk about 0, 1, and 2. So how are we able to write it? So first of all, how many permutations are there? So if we have n numbers, we have n factorial permutations. Okay, why? Because 0, so if we think about the first digit, the second digit, the third digit, in this case we can choose any one of the three, and if we fix this, then there will be 2 left, and if we fix this, there will be only one way of doing that. So it's 3 times 2 times 1 is 6. So it's 3 factorial. 3 factorial is 6. So that's the number of times we can write this. So let's start writing these down. So we can, so for these things we have 0, 1, 2, 0, 2, 1, 1, 0, 2, 1, 2, 0, 2, 0 1 2 0 2. Okay, so the reason they are written like this is because lexicographically, so that's lexicographically the first one always comes in sequence, then the second one and the third one and so on. So I think I see a pattern. Let's do the same thing for 0 1 2 3. So let's do it for this. So we have, what the hell, four different things, and we will take a look at the four different ways of permuting this. So first of all, how many ways are there in solving this? So there is 4 factorial, or 4 times 3 factorial, which is 24. So 24 different ways of solving this. Okay, so the first thing is it will start off with a bunch of zeros, 0 0. So we have to figure out how many zeros there's going to be. So the first one, okay, let's think about it. So there's the first one, second one, third one, fourth one, and there are 4 ways in which we can add a value here. We can add either a 0, a 1, or 2, or 3. So 4 ways of doing that, and the rest of it is 3 factorial. So there are 3 ways of doing that, 2 ways of doing that, and 1 way of doing that. So there are 3 factorial ways in which we can arrange the rest of the numbers given this. So this 3 factorial is 6. So we will have 1 2 3 4 5 6 zeros, and then 6 ones, 2 3 4 5 6 ones. Then we'll have 6 twos, 1 2 3 4 5 6, and then we'll have 6 threes, 1 2 3 4 5 6. That should give us 24. That should give us 24. So that's 1 2 3 4 5 6 7 8 9 10 11 12 13 14. You cannot see it, sorry. Okay, 14 15 16 17 18 19 20 21 22 23 24. So that's 24. Okay, the next one, this is where we see recursion happening. So the first one, if we group this as blocks of that, so if we have 0 over here, what we have is 1 and 2 and 3 remaining, 1 and 2 and 3 remaining, just like that. So we are going to have 2 factorial 1s, so 1 1, 2 factorial 2s, 2 2, and 2 factorial 3s, like that. Okay, and we will repeat this except over here. Okay, so now over here we have 0 2 3. Those are the things available to us. So we have 2 factorial, that's 2 factorial zeros, so 0 0, 2 factorial 2s, 2 2, and 2 factorial 3s, 3 3. Over here we have 0 1, and 3. So 2 factorial zeros, 0 0, 2 factorial ones, oh, this should be over here, this should be over here, ones, and 2 factorial 3s, like that. And over here we are left with 0 1 2, so we'll have 2 factorial 0 0 0, 2 factorial 1s, and 2 factorial 2s. Okay, so that's the general gist of how we go from here to here, here to here, here to here, and so on. So let's see whether we can generate this. Okay, so I think I know how to solve this problem. So now we need the millionth lexographic permutation of the digits this. We want to know if we are at point n is 9, for example, in this case, then what are the digits? Can we figure this out? So for this particular case, for the case of n equals 4, we can write out everything, and then based on that we can figure out what the results are. So now we have this, and then this, that, and then this and that, and now we only have 2 more combinations, 2 3 and 3 2, and so we had 1 2 3 over here, and 2 is taken, so 1 3 and 3 1, and over here it's 0 2 3, and over here 0 is taken, so we have 2 3. Oh wait, so we still have to solve this. This is 0 3, and 3 is taken, so it will be 1 2 and 2 1. Over here 1 and 0 is taken, so we have 2 3 and 3 2. Over here 1 and 2 is taken, so we have 0 3 and 3 0. Over here 1 and 3 is taken, so it will be 0 2 and 2 0, and we can fill the rest up. Okay, so we are concentrating on this. So let's figure out if we are given, oh, we should call this something else, and let's call this m. So we are given this value m equals 9, and we need to figure out what this combination is at this point. So the first value, m is 9, we know that and we have 0 1 2 and 3. We know 0 will happen, 0 will be written down in this case, n. So in this case n equals 4. So we have these things, n equals 4. Okay, if n equals 4, then we know 0 will occur 6 times, 1 will occur 6 times, and so on. So if m is 9, 9 minus 1 by this 4, we need 6, which is n minus 1 factorial. So that should give us how many time where we are with respect to this. Okay, so 9 minus 1 is 8, 8 and n, what is this? This is n minus 1 factorial. N minus 1 factorial is 3 factorial is 6. This in Python is integer division. So 6 goes in 8 once, 1, so that value is 1. So that's how we know that the first value is going to be 1. Okay, then we come over here, and this is the third value, or in index terms it's the second value. So I should do 9 minus 1 percentage n minus 1 factorial, n minus 1 factorial. So 6 goes to 8 one time, and then there is 2. So 8 percentage 6 is, oh, what am I doing? It's 2. So that's 0, 1, 2. Okay. Oh, wait. Now we know that it's 1. So wait, I think I have a better way of thinking about it. Let's think about it. So now we know that the first digit is 1. So that's the first digit. Okay. Now we have a new problem. N is 3, right? Okay. The list of things that we have is, we've taken the first digit out, so it used to be 0, 1, 2, 3. Now it's 0, 2, 3, and we have m should now be m will be nine minus 1 percentage n minus 1 factorial. So that this is the, we have to update this later, 3, and we have 0, 2, 3. Okay, so not here, not here. So 9 minus 1, so that's 2, that's 2, and I think we'll have to add 1 so that it becomes plus 1. I think we'll have to add, or we can just do we can, or we can just do 9. So m used to be, so m, this is m percentage n, m percentage n minus 1 factorial. So whatever we get, that becomes m. So now that we have m, and we reduce n by 1, and then we take a look at what else we have, and then we repeat the process. Okay, let's see whether we can code this up. I think this is how we can find the nth value without having to look at all the different permutations. Well, that is the idea. So let's see whether we can code it. I think if we I think this we will be able to solve this way. This looks like a more difficult problem than I had imagined. Okay, so let's try to solve this. So we have a list of, so let's take a look at this list. Numbers is 0, 1, 2, 3, and 4. We're going to take a look at the problem that we did with 4 numbers. 4 numbers, that looks like that. Okay, and the important thing is and I think it.permutations nums will give you all the permutations. Okay, but this one is going to evaluate every single permutations, but if we just an iterator will not have a I want to see if I can drop the first n. Start, stop. So I slice. So if I have I slice, this is what I want. I want the 10th value and 10th to 11th. Oh, can I do a list? Okay, how about the 0 and 1? 0 and 1. That. Okay. Will I be able to will I be able to use this if I, let's say nums is 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. If nums is that, and if I do this, it will give me that. If I do 1,000,001, that's a million. That's a million. 1,000,001 and 1,000,002. 2. Wow, I don't have to do all of this stuff. Wow. Let's see if this is the answer. I did all of this, and that appears to be incorrect. Okay. Oh, this may not be lexicographic. It can be anything. I think it doesn't have to be lexicographic. I think that's where the problem is. I don't think it's going to be numbers is that. List. Oh, it is lexicographic. Why will it not be? Okay, let's do a quick sanity check whether this makes sense. So, according to our, where did this go? Yeah. So according to, let me just use this. Okay. According to this, the first one is going to be 9 minus 1. So 4, 9, 8 factorial that's that number. There are 8 factorial zeros, 8 that many ones, that many twos, and so on. So if we do 1 million, if we have 1 million, um, 1 million minus 1. Okay. 24. That doesn't make any sense. Oh, it should be 9. It should be 9. 2. It is 2. So this is correct. And the number I entered is not correct. Okay. 1 millionth is okay. What is the millionth permutation of the digits? That it should be close to this number. I am pretty sure it should be really close to this number. And I am pretty sure the first so many digits are correct. Okay, so why don't we do this? We will figure this out by the no, this is correct. 1 million is in number. That's 6 zeros. So 1, 2, 3, 4, 5, 6. That is the millionth number, in the same way as that's the first number. Wait. That's the first number. I need 1 million minus 1. 1 million minus 1 and 1 million, like that. And it should be there, 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 and that should be the number. I have to wait 23 seconds. Let's see if this is the result. All right. So again, we see that Python libraries by themselves have the right tool. So I was supposed to do all of this stuff, but Python already, IT permutations, IT tools permutations actually does it for you, so you don't have to. So you have just advanced to level 1. 11% of the people have made it so far. Okay, it's good to know. Journey begins. Okay, so it was a little bit of a letdown, I guess, that the solution to this in Python is so simple. Let's look at maybe one more problem. If this problem is very simple, we might do one more problem beyond this. Okay, so this is problem 24. Let's look at the next problem. So this is problem number 25. problem 25. I did not copy this. That's problem 25. And let us just do this problem. Okay. This is an equation. That is an equation. And that looks like that. That looks like that. Oh, n minus 1. And like that. What the hell is this? Yeah, so that looks like an equation. F1 is 1. F1 is 1. And F2 is 1. Okay, so that's the Fibonacci sequence, and we all know what the Fibonacci sequence is. So if you have been coding for a while, then this will be very familiar to you. Depending upon, you can start with 0 or 1, the sequence will be different, but in this specific case, F1 is 1 and F2 is 2. Alright, the 12th term, F12, is the first term to contain 3 digits, so that's 3 digits. Okay, what is the first term in the Fibonacci sequence that contains 1000 digits? 1000 digits. Okay, I don't see why we cannot just loop through it. So I equals 1. Okay, and F1 Fi equals 1. So there's Fi and IP1 IP1, that's I plus 1 is 1. So we have the I equals 1, and we have the next sequence, and for whatever in range 20. Okay, I plus equal to 1, Fi, so that stuff. That equals so we shift 1, and the next one we add the 2 like that, and print F I, and I will put $5D, 5 justified, and I will put Fi. Okay, so 2 is 1, 3 is 2. I can even put F underscore I Damn. Never mind. This is not very good. Okay. We start with this and then we stop here. Okay. 2 is that, and so on. And 2 stop equals 3 digits. So we will look at 3 first. If length of str of fi is 3, this 2 stop, okay, equals I. Right, that's the answer. Okay, so I need to break as well. So let me put this over here. Okay, so the answer is 12, like it says over here. I want to make this while true, like that, and yeah, I don't think printing this is useful, except if I percentage 100 we equal 0, then print this. So every 100 items we will print to make sure that the program is running. So if we just do that, then with percentage, like that. Okay, now instead of to stop at 3, we want to stop at 1000. Okay, it did print something, so that's the answer. It stopped at 1000, and that is the Fibonacci number. You are the so manyth person to solve this problem. Okay, fairly simple. Maybe we can do one more problem, and okay, where are we? We are at problem number 25. Yeah, maybe we will stop here and then we can continue next time. Okay, so thank you again. I will be uploading this to YouTube, and if you like content like this, please like and subscribe, and I will see you next time. Bye bye.